a starship finally reaches another star. And that's when things get truly dangerous. The target has moved. You're still screaming in at a fraction of light speed. Your data is decades out of date. And there's no help coming from Earth. In this video, we'll break down what really happens next. Locking onto a moving star, braking without dying, crossing an alien heliosphere, scanning for life, and turning one arrival into the seed of a galactic civilization. Here's the core issue. The star you launch toward is not in the same place when you get there. During the 50 years you've been travelling at around 20% of light speed, the target star has been orbiting the centre of the galaxy at roughly 220 kilometers per second, about 490,000 miles per hour. That motion adds up to trillions of kilometers of displacement. If you point your ship at where the star was on launch day, you cruise straight past the system, and there is no way to turn around cheaply at those speeds, so you do not aim at the star's current position, you aim at its future position. Back at home, before launch, astronomers measure its distance and motion very precisely. They track its apparent shift on the sky over years, then use that to project its path decades ahead. The pointing tolerance is brutal. If you're off by a tiny angle, far smaller than the width of your finger at arm's length, that small error spreads out over light years, and at the far end you are millions of kilometers away from where you need to be. So how do you even get a position that precise when the star is just one bright pixel in a telescope? You rely on two very small effects, parallax and proper motion, and you measure them until the noise is squeezed out. Parallax is the apparent shift of a nearby star when you look at it from different points in Earth's orbit. In January, Earth is on one side of the Sun. In July, it is on the other side, about 1 astronomical unit away, roughly 150 million kilometers, 93 million cells. Against the distant background stars, the nearby star appears to move slightly. That angle is usually a few thousandths of an arcsecond, which is a tiny fraction of a degree. From that you get distance. On top of that you measure proper motion, how the star drifts across the sky year after year, because it has its own velocity in space. For nearby stars that drift is still small, maybe a few hundred thousandths of an arcsecond per year, but with space telescopes and long baselines you can track it, put distance and motion together, and you get a three-dimensional velocity vector for the star. Then you run the clock forward 50 or 100 years, and you predict where it will be when your starship arrives. Your ship's navigation system carries that prediction as part of its core map. As you coast through interstellar space, you compare what you see through your own telescopes with that predicted sky. If the angles between guide stars are off by even a tiny amount, you know your trajectory is drifting. But there is another complication. At 1/5 of light speed, even the sky itself is distorted by your motion. So here is the next question. What happens to your aim when relativity starts to bend your view of the universe? At around 0.2 times the speed of light, about 60,000 kilometers per second, 134 million miles per hour, relativistic aberration becomes important. Light from stars in front of you gets concentrated into a narrower cone around your direction of motion. The whole forward sky appears compressed, and stars that would normally sit off to the side seem to move closer to your heading. Stars behind you seem to slide away and dim. On top of that, their colours shift. Light from objects ahead is pushed towards shorter wavelengths. It is blue shifted. Light from objects behind is pulled toward longer wavelengths. It is red shifted. For your crew and your instruments, that means straight ahead is not the same as it would be at rest. If you try to steer by the raw positions of stars in the forward field of view, you will be off. Your navigation computer has to correct every measurement for your own speed. It must take the observed positions, apply the relativistic formulas, and recover where those stars would appear if you were stationary. Any small mistake in that correction, any error in your estimate of your own velocity, feeds directly into your targeting solution, and over light years, that error multiplies. So if the target is moving, and your motion is warping your view, what can you lock onto that is stable and predictable enough to trust? You turn to pulsars, rapidly spinning neutron stars that emit beams of radio and X-ray pulses with extremely steady timing. Many of them rotate hundreds of times per second. From your ship, you receive those pulses as a series of ticks. The interval between ticks is so regular that if one comes a few millionths of a second early or late, you know you have changed your distance to that pulsar by hundreds of kilometers. By monitoring several pulsars spread across the sky, you can triangulate your position in three-dimensional space without needing any artificial set of satellites. This method is already being tested conceptually for deep space navigation. For your interstellar ship, it becomes a core backup to the star catalogues you brought from home. You compare your pulsar-based position and velocity to the expected track, and if they disagree, you know that something, maybe a long-term thrust imbalance, maybe accumulated hits from the interstellar dust, has nudged you off your original plan. You then schedule small trajectory corrections to bring the two into alignment again. But even with all of that, you still face the most sensitive phase of targeting, the final correction before you enter the new system, when tiny pushes decide everything. Here is the paradox. The closer you get, the smaller the maneuvers, but the higher the consequences. At a distance of 1 light year from the target, that is about 10 trillion kilometers, more than 6 trillion miles. A change in your sideways velocity of just 1 millimeter per second, 1,000th of a meter per second, can shift your path by millions of kilometers by the time you reach the star. That tiny tweak is less than the speed of a crawling insect, but over the remaining distance it becomes the difference between threading through the orbits of planets and missing them completely. So, hours or days before arrival, your ship fires extremely fine control thrusters. These are not big main engine burns, just gentle, carefully timed bursts that trim your trajectory. Your guidance system fuses every source of data you have, the old Earth-based astrometry, your in-flight star measurements, your pulsar timing, and the relativistic corrections, and it picks a final arrival path. You commit to that path because at this point, you do not have the spare propellant or the time to change your mind later. The unsettling part is that a lot of this still rests on measurements made decades earlier, back in the home system, with instruments that no one on the ship has ever seen. If a catalogue entry was wrong, if a binary companion to the target star was missed, and the motion was slightly mismodelled, your perfect final burn can deliver you to empty space. The navigation math can be flawless, and the input data can still betray you. So when you finally cross the outer edge of the target star's domain, and your sensors confirm that you really did hit the moving target, you have solved only the first problem of arrival. You are now rushing into this new system at a huge fraction of light speed, carrying kinetic energy on the scale of planet-destroying weapons. The next question is even more unforgiving. How do you actually slow down from 0.2 times the speed of light without tearing your starship apart? You reach another star at around 0.2 times the speed of light, and the first hard fact is this: you're carrying the energy of a major warhead stockpile in your own motion. At roughly 60,000 kilometers per second, about 134 million miles per hour, a starship with a mass of 1,000 tons, about 1 million kilograms, holds kinetic energy on the order of 10 to the power of 21 joules. That's in the same ballpark as tens of thousands of megatons of TNT. Stopping is not just tapping the brakes, it's safely getting rid of the energy that could strip a planet if you dumped it in the wrong way. And you have to do it while keeping your structure, your crew, and your destination intact. This is why a pure rocket burn to zero solution is almost hopeless. To throw that much energy away with engines, you either need an absurd amount of propellant, or engines so powerful that any failure cooks the ship. A high thrust burn also slams your crew with high G for long periods. Even 1 G, about 10 meters per second squared, feels like Earth gravity, and doing that for days or weeks straight on top of a fragile interstellar hull is brutal. So you look for ways to trade speed for time and distance to let the universe itself push back on you, slowly but over months and years. So the next question is, how do you use the star you're approaching as your brake, instead of your target to crash into? One tool is a magnetic sail or magsail. You run a strong electric current through big loops of wire, or you use superconducting structures, and you generate a magnetic field that can stretch out hundreds, even thousands of kilometers around your ship. You're not inflating a physical sail, you're inflating a magnetic bubble. When you move into the target star's charged particle wind, a stream of protons and electrons flowing out at maybe hundreds of kilometers per second, that wind hits your magnetic field and is deflected. Every particle that bounces off transfers a tiny bit of momentum to your field, and that momentum flows back into your ship as a braking force. The deceleration here is very low, maybe a fraction of a millimeter per second squared, far less than 1,000th of a g. You would not feel it as weight, but you do not need to feel it. Over months and years, that tiny, steady push can cut tens of thousands of kilometers per second off your speed. The big advantage is you don't burn propellant. The star supplies the reaction mass. The downside is you have to arrive with your trajectory lined up so you have time and distance for the magsail to work, and your hardware has to survive a huge, delicate, energy-rich magnetic structure without tearing itself apart. But what if your ship did not use rockets at all to accelerate, and you came in on something even stranger? A lightsail driven by a laser. In that case, you might carry a huge, thin, reflective sail, possibly hundreds of kilometers across. On the way out of your home system, a giant laser array pushed on this sail with light pressure. Photons have no rest mass, but they do carry momentum, and when they bounce off a mirror, they transfer a tiny shove. Billions and billions of photons per square meter add up, and over time you can get to a significant fraction of light speed. Now, approaching the destination star, you can try to use photon braking in reverse. Flip the sail so that the incoming starlight hits the reflective side. At 1 astronomical unit from a sun-like star, the incoming solar flux is about 1.3 to 1.4 kilowatts per square meter. A perfectly reflective sail fills twice the light pressure, because photons bounce rather than get absorbed. Multiply that by a sail area of tens of thousands of square kilometers, and you get a continuous but low thrust in the opposite direction to your motion. Again, the numbers are small per second, but relentless over months. You gradually bleed off speed using nothing but light. This method is extremely sensitive to your approach path. If you come in at the wrong angle, the geometry between your velocity, the star, and the sail normal doesn't give you useful braking. If you get too close, the thermal load and the risk of tearing the sail in uneven radiation pressure goes up. If you stay too far, the light is too weak. You are threading a needle in 3 dimensions, with a sail that could be larger than some countries. Even with magsails and light sails, you may still want help from gravity itself, which leads to one of the most dangerous tricks in the whole arrival sequence, a stellar gravity assist. Here, instead of trying to stop dead, you dive into the star's gravity well on a carefully shaped hyperbolic path. As you fall inward, you speed up relative to the star, but your direction of motion bends. If you time it correctly, the path you take through the well lets you trade some of your forward speed, relative to the rest of the system, for a different trajectory, maybe a bound orbit that keeps you in the system rather than flying straight through and out. The closer you skim to the star, maybe just a few stellar radii above the visible surface, the more your path bends. But the closer you go, the more intense the heat, the radiation, and the tidal forces across the length of your ship. Temperatures can climb high enough to test your heat shielding to the limit. Unequal gravity between the bow and the stern of the ship can try to stretch or compress your structure. If your navigation is off, you either pass too high and don't lose enough speed, getting slingshotted out even faster, or you pass too low and you fall into the star, or at least into layers so hot and dense that your hull cannot survive. So you are trading a massive propellant bill for a massive demand on navigation precision and structural toughness. You are literally converting deadly straight-line velocity into thermal stress and orbital reshaping and hoping your numbers are right. All of these methods, magnetic sails, photon braking, gravity assists, share one brutal consequence. The energy has to go somewhere, and most of it ends up as heat in your systems. Your radiators, those big panels or booms that dump waste heat into space. Now, have to handle power levels in the gigawatt range, maybe more. They might glow red hot, then white hot, running at temperatures of thousands of Kelvin, thousands of degrees Celsius, while still staying structurally sound. They have to radiate away the unwanted energy fast enough that your core systems do not overheat. The magnetic coils of your magsail carry huge currents and sit in changing fields which induce mechanical forces and heating. The lightsail has to survive intense flux without melting, tearing or wrinkling. On top of that, your main structure, the trusses and tethers that hold big components together, sit under continuous low-G deceleration, maybe 1/100th of a G or less, for months. That is not much weight per square meter, less than a sheet of paper resting on your hand, but applied over kilometers of span, any small flex can grow into a vibration. If those vibrations line up with the natural resonant frequencies of your ship, they can amplify like pushing a child on a swing at just the right rhythm until parts start to fatigue and crack. So during braking, your control systems are constantly watching for tiny oscillations, shifting thrust directions, retuning magnetic fields, and moving masses around inside the ship to change the resonance pattern. If you get it wrong, you do not just overheat, you can literally shake yourself apart while trying to slow down. And even if you manage to dump that energy without breaking your ship, at the end of this whole process, you are still not safe. You have dropped from a lethal interstellar speed to something you can live with, but now you're about to cross into a new kind of space, the outer edge of an alien star's influence, where the environment itself changes from almost pure vacuum to a charged, moving plasma. So the next problem is simple to state and hard to handle. What happens when you cross that invisible border from the thin interstellar medium into the dense, chaotic bubble of an unknown heliosphere? You spend decades in almost empty space, then in a very short span your environment stops behaving like a vacuum and starts acting like a storm. Nothing looks different through a window, but your instruments see the line, and once you cross it, you're no longer in the galaxy's general background, you're inside one star's territory. Out between stars, the interstellar medium is incredibly thin. You may have between about 0.1 and 1 proton in each cubic centimetre, so a volume the size of a sugar cube holds just a handful of particles. There are magnetic fields there too, but they are weak. They drift slowly, and for the most part your ship can treat this region as empty. Your shielding, your electronics, your communications have all been tuned for that desert. As you approach the new star, that changes. The star throws out its own wind of charged particles, mostly protons and electrons, racing outward in all directions. Where that wind pushes hard enough, it carves out a bubble in the interstellar medium. When your ship hits the outer layers of that bubble, your plasma sensors start reporting a clear trend. The number of particles around you begins to climb, and the magnetic field suddenly has a preferred direction, tied to the star's rotation and its own magnetic poles. You still feel weightless, but your data streams spike. Detectors that were counting only a few particles per second now see tens, then hundreds. The energy spectrum shifts. You see more of the lower energy particles from the stellar wind, and your computers flag the change. You have crossed into the heliosphere of an alien star. Now you're dealing with that star's personal space weather, not just the galaxy's background. The obvious question is, how far out does this bubble actually reach? And how long can you be inside the system before you even see anything that looks like a system? In our own case, the Sun's heliosphere extends to roughly 120 astronomical units in the upwind direction, the direction we are ploughing into the local interstellar medium. That is about 18 billion kilometers, around 11 billion miles from the Sun, almost 4 times the orbit of Neptune. Downwind, the bubble probably stretches into a long tail, hundreds of astronomical units long. That's our middle-aged, fairly calm G-type star. A more active star with a stronger wind or higher magnetic activity could inflate a larger bubble. A quieter star, or a star moving through a denser patch of interstellar gas, could be squeezed into a smaller one. Your Starship doesn't know in advance, it has a model. but the real boundary only appears in your data when you hit it. Once you do, you might still be decades of coasting away from seeing the star as more than a point of light. Colonists might feel like they have arrived because technically you are inside the star's sphere of influence. But practically, the planets and the bright disk are still far out of reach. And that boundary is not a clean, thin shell. It can have structure, and that structure tells you a lot about the star you're dealing with. As the outward stellar wind hits the interstellar medium, it is usually moving faster than the local speed of sound in that plasma, so it can form a shock, where the flow slows down abruptly and heats up. In our solar system, spacecraft like Voyager 1 and Voyager 2 have already passed through the sun's termination shock. Their instruments saw the particle speeds drop, the temperature go up, and the magnetic field lines kink and twist. Your Starship now performs the same experiment but around another star. When you cross the termination shock, you measure how big the jump is in density and temperature. Are you seeing a gentle slowdown or a brutal one? You map how chaotic the magnetic field becomes in that region. You look for a bow shock farther out, where the whole heliosphere plows into the interstellar gas, like a ship's bow wave. From these profiles, you back out how strong the stellar wind is, how variable it is over time, how often it probably flares. That feeds directly into your judgment about what kinds of planets inside this bubble can hold atmospheres, and how stable their climates might be over billions of years. But those are still abstract plasma numbers. The next step is more personal. You translate this environment into actual radiation doses for human bodies. In the interstellar medium outside any heliosphere, you're exposed to a relatively high flux of galactic cosmic rays, very energetic particles that have been accelerated by supernova and other extreme events. They can deliver hundreds of millisieverts of dose per year to an unshielded person, which is a serious health risk. Inside a strong heliosphere, the star's magnetic field and wind can deflect many of those cosmic rays, cutting their intensity significantly. So one of the first questions you answer after crossing the boundary is, did the dose rate go down? However, you do not get that protection for free. A more active star that gives you strong shielding against cosmic rays may also produce frequent, violent flares and coronal mass ejections. Those events throw out their own bursts of high-energy protons and heavier ions, which can hit you in sharp spikes. Instead of a steady, high drizzle of radiation, you might be facing sudden storms that for a few hours push the dose rate to levels that are immediately dangerous. So your dosimeters, the devices that measure radiation on board, are watched as closely as your navigation sensors. You convert those measurements into sieverts per year and compare them with known human limits. For reference, current space agencies often think in terms of a career limit of about 1 sievert for an astronaut, total due to long-term cancer risk. If you are seeing something like 0.05 sievert per year on the surface of a shielded habitat, that is manageable with smart engineering. If the baseline or the flare spike suggests several sieverts per year even undercover, that zone becomes a red line. You mark regions, orbits and worlds as safe with shielding and safe only underground, or no-go before anyone steps outside. And while you're tracking invisible particles and field lines, the physical solid threat at this boundary starts to grow too. Dust and debris. Far out in interstellar space, dust is rare. A few atoms of solid material per cubic meter. Your forward shields may be layers of ice and metal foam a few meters thick, or an electromagnetic deflector that charges and pushes dust grains aside, handle occasional hits. But as you move deeper into the heliosphere, especially toward the plane where that system's planets and asteroids orbit, the number of real grains increases. You start to see particles the size of smoke, then sand, then pebbles. Now connect this to your speed. Even after heavy braking, you might still be moving at 1% of light speed when you first cross the boundary, around 3,000 kilometers per second, about 1.9 million miles per hour. At that speed, a grain of sand, a fraction of a millimeter across, carries kinetic energy similar to a small explosive when it hits your hull. It will not just make a dent, it can vaporize material on impact and send shockwaves through whatever it hits. Your shields now face a much higher impact rate. Sensors in the leading layers listen for hits, count them, and build a real-time map of dust density as a function of direction. If the rate spikes, your navigation team has to make choices, turn the ship to bring fresher shield sections into the path, adjust your speed profile, or change your approach plane to avoid known dust belts. Thin structures, like antenna masts, radiator edges, and parts of your magsail or lightsail hardware, are especially at risk. A single larger grain could slice through them. So you run in a new mode. Every kilometre you advance, the environment gets more cluttered, and every impact is a small test of your engineering. This is still only the outer border of the system. You have not yet resolved a single planet as more than a dot, but already the plasma, the radiation, and the dust are forcing you to redraw your plans. And as that outer chaos settles into something you can handle, a new question starts to dominate, now that you're through the border and still in one piece. How do you turn this anonymous star and its unseen planets into a detailed, actionable map of actual worlds you can use? You spent decades seeing this star as a single pixel, then over a few billion kilometers, it suddenly turns into an entire family of worlds. That switch from one dot to full system is the moment your mission either becomes science fiction level powerful or blind and dangerous. Once you're inside about 10 astronomical units, roughly 1.5 billion kilometers, about 900 million miles from the star, your telescopes and interferometers finally stop seeing just a point. Interferometers link multiple telescopes across your ship with precise timing, turning their whole separation into one giant virtual mirror. The bigger that baseline, the finer the details you can resolve. At this distance, that's enough to start separating planets from the glare. Big, hot gas giants close to the star show up first. They glow strongly in infrared, so your IR cameras pick them out as bright blobs against the cooler background. Farther out, you catch cooler Neptune-like worlds, then fainter, smaller objects down toward Earth, size and below. From Earth, trying to see an Earth-sized planet tens of light years away is like trying to spot a firefly right next to a stadium floodlight from another city. From here, you're sitting inside the parking lot. The contrast problem is still hard, but no longer absurd. Your first full system image looks less like a solar system diagram and more like a radar screen, dots and arcs with error bars. But for the first time, you're not guessing which worlds are there. You are literally pointing at them. That instantly upgrades every decision you make next, from safe approach lanes to where you might land. But seeing dots isn't enough. You need to know where these planets are going, how heavy they are, and whether their paths are stable over long times. So the next question is, how do you turn those faint points into precise orbits, in real time, while you're still falling in? You start clocking transits, planets passing in front of the star and dimming it slightly. From this close, you can time those dips down to seconds. A planet with a 1-year orbit should cross the star on a precise schedule. If that timing shifts by tens of seconds, that tells you other planets are tugging on it gravitationally, speeding it up or slowing it down a bit. That's called transit timing variation, and it lets you detect worlds that might be too small or off-angle to see directly. At the same time, you use high-precision spectroscopy to measure the star's wobble. As planets orbit, they pull the star around a tiny orbit of its own. Along your line of sight, that wobble shows up as tiny shifts in the star's spectrum, corresponding to speeds of maybe 1 or 2 meters per second walking speed, compared to the star's 200,000 meters per second, or about 450,000 miles per hour, as it orbits the galaxy. From far away, those meter per second signals are buried in noise. From here, with shorter light paths and better photon counts, you can dig them out and tie them to the specific planets. Put the transit timing and the wobble data together, and you get both masses and orbits. You can say this one is 3 times Earth's mass, this one is a hot Jupiter on a 3-day orbit, this one is a super-Earth hugging the inner edge of the habitable zone. Now you know where the deep gravity wells are, where stable parking orbits might be, and which paths are chaotic. But mass and orbit still don't tell you the key thing: what does the surface of these worlds actually feel like? So the next step is blunt. Are these planets frozen, mild, or hellish? And how do you tell without going down there? You turn to infrared again, but this time as a thermometer. Every object with a temperature above absolute zero emits thermal radiation. The spectrum and intensity tell you how hot it is. You measure emission from each planet at wavelengths of a few micrometers, the thermal infrared, and fit it to models. A bare rock at about 1 astronomical unit from a sun-like star with no atmosphere should settle at something like 255 Kelvin, about minus 18 degrees Celsius, 0 Fahrenheit, as a simple black body. If you instead measure closer to 288 Kelvin, around 15 Celsius, 59 Fahrenheit, you know something is trapping heat, likely an atmosphere with greenhouse gases. You do this across different phases, when the planet shows more day side or more night side. Large temperature swings hint at thin air and low heat capacity like Mars. Smoother curves hint at thick atmospheres and possibly significant oceans or cloud cover. Suddenly, climate models that were just lines of code for Kepler planets are being tested against real close-up data. Some of your best candidates from home may turn out to be overheated, thick cloud ovens, while some dull-looking dots in the outer zone turn out to have surprisingly warm surfaces thanks to internal heating or dense air. Once temperatures are on the table, the next issue is context. A planet can be in a nice orbit and still be in a shooting gallery. So you ask, how chaotic was this system's formation, and is it still throwing rocks around? You probe for rings, moons, and debris. When a planet passes in front of the star, you don't just look for one clean dip in brightness. You look for multiple small steps and wiggles, which can signal rings tens of thousands of kilometers wide, or big moons crossing just before or after the main planet. You watch for occultations too, cases where a planet, moon, or ring passes in front of background stars. That tells you about their sizes and shapes with very high precision. Farther out at tens of astronomical units, you look for broad, cold dust belts, like our Kuiper belt, or even more massive structures. In infrared and sub-millimeter wavelengths, they show up as diffuse bands. Their structure matters. Sharp gaps can mean giant planets have migrated through and cleared paths, throwing smaller bodies around like shrapnel. A smooth, faint belt hints at a quieter history. If you see multiple belts and strong asymmetries, you know this system has had, or still has, major rearrangements. That feeds directly into risk, because dynamically hot systems are more likely to send comets and asteroids into the inner zone, straight across the orbits you might want to use. Now you have orbits, masses, temperatures, and a violence score. That sets up the most disturbing question of this whole scan. Are you alone in this system, or are you dropping into someone else's infrastructure? This is where you start hunting for techno-signatures, signs of technology rather than geology or simple biology. You point radio arrays at the star and its promising planets, and you look for narrowband signals, emissions concentrated at very specific frequencies, much thinner than natural noise usually is. You scan optical and near-infrared bands for brief intense spikes that could be laser flashes, used for communication or power beaming. You examine the infrared output of the system as a whole and check whether any region is brighter in waste heat than it should be, given the starlight it receives. A partial Dyson swarm, a big orbital power network, would intercept a lot of light and re-emit it in mid-infrared as heat. Even a power beam of just a few gigawatts, spread out over light years, might show up to your instruments as a suspiciously clean line in the spectrum with no obvious natural explanation. You cross-check for modulation, patterns that look like data encoding. If you find something even slightly convincing, your mission profile flips. This is no longer just a colonization and survey job, it's a first contact, or at least a don't blunder into someone's power grid job. You start planning no-go zones around potential artificial structures, and your odds of being observed yourself go way up. And all of this, the family portrait, the orbits, the climates, the debris, the possible technology, is still being done while you are on a hyperbolic path, not yet captured. You've turned the star from a single dot into a full map of worlds, but right now you're just a fast-moving visitor who will shoot past and never come back unless you do something drastic. So the tension jumps to the next question. Now that you finally know what's here, how do you actually grab onto this system's gravity and claim long-term orbits, instead of just doing a one-time flyby at interstellar speed? You arrive as a bullet, not a neighbour. Your path right now is a hyperbola, an open curve that cuts through the system once and then heads back into deep space forever. If you do nothing, you will never come back to this star. To stay, you have to change that open path into a closed loop, an ellipse, and that means you have to kill just enough velocity in exactly the right direction to let gravity grab you. By this point, you've already dropped most of your interstellar speed, but you're still moving fast compared to local orbital motion. Around an Earth-like orbit, planets move at about 30 kilometers per second, roughly 19,000 miles per hour. You might still be coming in tens of kilometers per second faster than that. The good news is, you don't need to erase all of that. Sometimes a burn of just 1 kilometer per second, about 1,000 meters per second, around 2,200 miles per hour done at the right place, is enough to tip you from unbound flyby into bound resident. The key is timing and direction. You want to fire your engines near periapsis, the closest point in your current path to the star or to the planet you're targeting, because that's where a small push changes your whole orbit the most. Point your thrust opposite your direction of motion, shave those crucial meters per second off your speed, and your exit path swings inward, closing into an ellipse. Miss the burn window by a few minutes, or mispoint your thrust by a fraction of a degree, and your new orbit can end up too high, too low, or still unbound. In the worst case, you waste precious propellant and still get thrown out into interstellar space. So once you've fought your way from hyperbolic visitor into at least one stable orbit, you hit the next problem: where in this whole gravity field can you safely park your hardware so it doesn't get stripped away or flung out over time? That's where heliospheres come in. The heliosphere is the region around a planet where its gravity beats the star's gravity for the purpose of keeping satellites bound. For an Earth-mass planet at about 1 astronomical unit from a Sun-like star, that radius is on the order of 1.5 million kilometers, nearly 1 million miles. Inside that bubble, if you put a satellite into a reasonable orbit, the planet's pull dominates. Outside it, the star wins, and orbits around the planet become unstable. You use these zones as your basic real estate map. Around each major planet, you mark its heliosphere, then you pick orbits within those zones for your relay satellites, fuel depots, and early stations. Far enough out that they're cheap to reach from many directions, but deep enough inside the heliosphere that the star's tidal forces don't slowly stretch their orbits until they escape. For gas giants with huge heliospheres, you may end up with layers of infrastructure, communication shells, navigation beacons, and tugs, all living in that gravitational pocket. But even inside a planet's heliosphere, you still want spots that are especially stable and cheap to stay in. So the next question is, are there natural parking spots in this three-body tug-of-war that you can exploit? Those are the Lagrange points. For each planet-star pair, there are 5 special positions where the gravitational pulls and the orbital motion balance out in a useful way. L1, L2 and L3 are along the line connecting the star and planet, and they're only marginally stable. L4 and L5, though, sit 60 degrees ahead of and behind the planet in its orbit, forming the corners of equilateral triangles with the star and planet. L4 and L5 are stable wells like shallow dimples in the gravitational landscape. Objects parked there tend to stay put, slowly circulating around the point but not drifting away easily. In our own solar system, Jupiter's L4 and L5 are full of Trojan asteroids, natural debris that's been trapped there for billions of years. In this new system, you may find the same thing. Clouds of rock and ice already gathered in piles that are much easier to mine than random asteroids on scattered orbits. You target these L4 and L5 regions as prime addresses for depots, big telescopes, early habitats, and traffic control hubs. Energy costs to move between an L4 or L5 point and the planet's orbit are low, and you get a wide, stable vantage point on the rest of the system. But as you start stacking hardware into these zones, another risk ramps up fast. You're populating an orbital environment with junk, and you might not be the only ones who have ever done that here. So the next issue hits you hard. How do you keep your spacecraft from colliding with natural debris? Or, in the worst case, with leftover infrastructure from anyone else who was here first. Even around a single Earth-like planet, orbital space is not empty. Natural debris, small moons, and human-made junk back home have already taught us that a 1 centimetre bolt at typical low-orbit speeds, 7 to 10 kilometers per second, about 15 to 22,000 miles per hour, can punch through metal panels and cripple satellites. In a new system, you might be dealing with denser asteroid belts, ring systems, or even artificial swarms of hardware. Your first move, once you're in bound orbit, is to start building a debris catalogue. You ping the sky with radar, you sweep it with optical and infrared telescopes, and you track every object you can detect down to tens of centimetres across. You fit orbits to them, you predict their future paths, and you assign collision probabilities with your planned stations and transfer routes. Any high-risk orbit gets flagged for avoidance. In some cases, you'll plan active cleanup, nudging small rocks or derelict machines into safer orbits, or controlled impacts. Traffic rules emerge fast. You define highway lanes in orbital altitude and inclination, routes that are kept clear for high-value or large vehicles. You restrict certain crowded orbits to small maneuverable craft that can dodge last-minute hazards. Your navigation computers run continuous conjunction analysis, checking for close approaches days, weeks, and months ahead, and scheduling tiny burns to slide out of the way. This is not optional. A single untracked rock can kill a station. A chain reaction of collisions can render a whole orbit unusable, like a Kessler syndrome on a new scale. But even with the best catalogues and strict traffic control, you're still only seeing a short slice of time. Some orbits are safe today and lethal tomorrow, just because of how gravity in a multi-body system slowly rearranges everything. So you're forced into a longer, more unsettling question. Which of these orbits will still be usable in 10,000 or a million years? That's where full N-body simulations come in. You take every major mass in the system, the star, the big planets, large moons, dense belts, maybe even shared Trojan swarms, and you let a supercomputer, or whatever your ship's upgraded version of that is, run their mutual gravitational pull forward in time. You don't just check the main planets, you check the orbits you care about, your proposed station sites, your planned transfer paths, your favourite Lagrange points. Over millions of simulated years, tiny resonances can show up. Places where a small push from a big planet, repeated on a regular cycle, slowly stretches or shrinks an orbit. Slight inclinations between planes can add up, pumping an orbit into more and more eccentric shapes, until it crosses other paths or dives too close to the star. Moons can suffer the same fate. A small moon that looks perfectly safe today might slowly spiral inward, hit a tidal limit, break into a ring, and send debris sweeping through the very orbits where you were planning to put habitats. Those results push you to make hard choices. You do not build your main base on a moon that your simulations say will migrate into a dangerous resonance in a few 100,000 years. You don't anchor your central depot in an orbit that looks clean now but drifts into a debris belt later. Instead, you pick locations that stay boring in the models, orbits that just slowly precess or wobble, but don't cross other major paths or amplify into chaos. By the time you're done, you've turned we're in orbit into we own specific stable gravitational plots around this star. You have insertion burns behind you, heliospheres mapped, Lagrange hubs picked, debris lanes marked, and long-term stability checked. You've carved out orbital high ground, but all of this is still about rocks and gravity and metal. The next layer is more brutal and more personal, because even if your orbits are perfect, the question that decides whether people can actually live here is simple. Does this system's radiation and atmosphere profile let human bodies and human technology survive for long, or are you about to drop down into a slow, invisible killing field? You've grabbed stable orbits and carved out safe traffic lanes, but that still doesn't tell you the one thing people care about most. Can anything living actually stand on these worlds without being cooked, choked, or irradiated to death? The first tool you use is the planet's own air, or lack of it, written in the light from the star. When a planet passes in front of its star, Some of the starlight filters through the thin ring of atmosphere at the edge of the planet. Your spectrometers break that light into colours very precisely, and you look for tiny dips at very specific wavelengths. Oxygen leaves a fingerprint around 0.76 micrometers. Water vapour leaves bands around 1.4 to 2.7 micrometers. Carbon dioxide shows up near 4.3 and 15 micrometers. Even if these gases are only a few parts per million of the atmosphere, these fingerprints can stand out because atoms and molecules absorb those colours very strongly. A nitrogen-oxygen mix, like Earth's air, has a very different pattern from a thick carbon dioxide-dominated atmosphere like Venus. So from orbit, you can already sort planets into broad types: breathable candidate, thick acid greenhouse, thin near vacuum. This is not subtle. Venus-type spectrum screams that you're dealing with crushing pressure and extreme heat long before you risk sending anything down. But knowing which gases are present is only half the story. You still need to know how much of that atmosphere is sitting on the surface and how hard it is trapping heat. So the next question is simple. Is the air here a gentle blanket, or a hydraulic press in an oven? You estimate surface pressure and greenhouse strength in a few ways. One is scale height, basically how quickly the air thins as you go up. That depends on the planet's gravity, the average mass of the gas molecules, and the temperature. By watching how the planet's apparent size changes at different wavelengths during transits, you can tell how puffy the atmosphere is, which tells you something about pressure and temperature together. You combine that with broad thermal emission measurements, the same infrared thermometer trick from before, but now tuned with better models. A thick carbon dioxide atmosphere, tens of bar deep, can trap so much heat that surface temperatures go above 700 Kelvin, over 430 degrees Celsius, around 800 Fahrenheit, like Venus. No human or normal equipment survives long there without insane protection. At the other end, a Mars-like atmosphere, less than 1% of Earth's surface pressure, can't hold heat or block radiation. That gives you a cold desert with brutal daily temperature swings and very little shielding from high-energy particles. So for each candidate planet, your computers spit out a basic verdict: surface pressure too high, surface pressure too low, or in a range that might support liquid water and human operations with the right gear. But the air and the pressure are only one side of the threat. The star itself can turn a just right planet into a long-term hazard by constantly blasting it with flares. That brings you to the next key issue. Is the star's activity something a planet can live with? Or is it basically a slow sterilization machine? Cooler red dwarf stars, for example, can be extremely violent, especially when they're young. They can fire off flares thousands of times more energetic than typical solar flares from our sun, flooding nearby planets with X-rays and extreme ultraviolet light. If your habitable zone planet orbits close in, which it has to around a dim star, it sits right under that gun. Even sun-like stars can have active periods where flare rates and coronal mass ejections spike, so you park your telescopes on the star and measure. How often do flares happen? How strong are they? How much high-energy radiation do they throw at different orbital distances? You run these statistics against the orbits of your potentially interesting planets. Are they being hit with sterilizing blasts every few million years, wiping out complex life before it can settle? Or is the flare activity moderate, something a decent atmosphere and a magnetic field can handle, like Earth has done for the billions of years? That last phrase matters because the planet's own magnetic field can make or break its surface environment. So the next question is, are these worlds naked under the stellar wind, or do they have invisible force shields like Earth's magnetosphere? You can't see a magnetosphere directly, but you can see what it does to charged particles. You fly probes through the planet's space environment and watch how the incoming stellar wind is bent. Around Earth, the planet's magnetic field pushes the solar wind away, carving out a magnetosphere that stretches tens of Earth radii toward the Sun and much farther into a long tail behind. Around Mars, which has only weak patchy fields, the solar wind slams almost directly into the upper atmosphere, stripping it over time. By mapping particle flows and field lines around your target planet, You estimate the size and strength of its magnetosphere. A big, robust bubble means high-energy particles are being deflected around the planet, not straight into the atmosphere or down to the ground. In practice, that can cut radiation flux at the surface by factors of 2, 5, even 10 or more, depending on latitude and storm conditions. That might be the difference between needing a thin roof and a little soil over your habitat, versus having to build deep underground or inside rock just to keep dose rates survivable. Finally, you turn all of this into a number that mission planners, doctors, and engineers can argue about in the same language: actual radiation doses per year, at real locations where people might stand. You convert particle fluxes and energies into sieverts per year, a unit that accounts for biological damage, not just raw energy deposited. For comparison, many space agencies today think of career limits for astronauts on the order of 1 sievert, total, over their working life in space. On Earth's surface, most people get a few millisieverts per year from background sources. In deep space, unshielded, a person might pick up a few hundred millisieverts per year. So you run the numbers for this new system. On the surface of an unshielded planet with a decent atmosphere and magnetosphere, you might see dose rates of maybe 0.05 sievert per year, 50 millisieverts, which is high but manageable with building design, local shielding and time limits. On a bare rock with no air and no field, or on a world under a hyperactive star, you might see several sieverts per year. At that point, you're talking about life-threatening doses in a few years or less, without heavy shielding. These maps don't stay in a science report. They become your zoning laws. Regions, orbits, and surfaces get tagged as no-go, short stays only, build under meters of rock, or okay for long-term colonies with standard protection. Before a single lander drops, you know that some beautiful planets are permanent red zones, and some boring-looking moons are actually prime real estate because they sit in safer radiation pockets. By the time you're done with this step, you know which worlds have air you can work with, how thick that air is, how angry the star really is, whether magnetospheres protect the ground, and what the actual human dose limits look like. You've answered, can anything survive here, in hard numbers. But there's another filter still waiting, because a planet can have good air on paper, tolerable radiation, and stable orbits, and still be useless to you if you can't get water, ice, and solid ground that won't swallow or shatter your landers. So the next problem cuts right to operations in this entire system. Where can you actually put metal on the ground, dig in, and find the raw stuff, water and rock, that lets a colony live without constant resupply from a star you left decades ago? You know which worlds have tolerable radiation and decent orbits, but that still doesn't tell you where you can actually land and live. The next filter is brutally practical. Where is the water? Where is the rock? And what happens to your ship when its landing legs hit the ground? From orbit, your first job is to find the volatile gold mines, the places with water, ices, and useful carbon-rich material. You scan surfaces with radar, bouncing radio waves off the ground to see under dust and into shallow layers. You run infrared and gamma-ray spectrometers to pick up the unique signatures of water ice, hydrated minerals that have water locked in their crystal structure, and organics, carbon-based compounds that can feed chemistry and industry. You pay special attention to permanently shadowed craters at the poles of airless moons. These spots never see direct sunlight, so ices that would boil away elsewhere can sit there for billions of years. A single large crater might hold billions of tons of ice, enough for drinking water, life support, radiation shielding, and rocket fuel if you split it into hydrogen and oxygen. But not every trace counts. You're looking for deposits that are at least a few % water by mass, not just a microscopic Mondstag smear. Anything less, and the energy cost to dig, heat, and purify that material is too high for a young colony. Once you've found promising patches of ice and rock, the next question is simple and unforgiving. What does gravity do to you and your hardware when you try to land there? Surface gravity sets the basic weight of everything you do. On a Mars mass world, you might feel around 0.4 g, roughly 4 meters per second squared. Your body feels lighter, Walking is easier, and landing burns are cheaper in fuel. On a super-Earth, you might be facing 2G, around 20 meters per second squared. That doubles your weight, doubles the load on your skeleton and heart, and multiplies the stress on every strut and bearing in your landing gear. At 2G, even standing up is a workout, and a fall is twice as hard. For vehicles, every touchdown in high gravity needs more thrust to slow down, which means more propellant and more heating. You compare gravity maps with terrain data. A rough mountainous surface under high gravity is a bad combination, steep slopes and hard impacts. You pick landing zones where this gravity is manageable and the topography is flat enough that your ship will not topple or slam down on a rock spine. Even then, one big unknown remains right under your feet. What is the surface actually made of, and will it hold you up or swallow you? That's where regolith physics comes in, the study of loose surface material, dust, sand, gravel, grain size, how sticky the grains are, and how much empty space sits between them, all decide whether your lander's feet dig in a few centimeters or sink meters deep. During Apollo, landers sat on lunar regolith with bulk densities around 1.5 grams per cubic centimeter, basically fluffy but solid enough to hold them. Comet 67P, by contrast, has an overall density around 0.5, closer to aerated foam. If you put a heavy ship on material like that, it can compact and collapse under you. So before you risk your main vessel, you send small probes. They carry penetrometers and load cells in their legs, measuring how the soil compacts under pressure. They fire small test thrusters close to the ground and watch how much material gets blasted away. You feed all that into models so you don't find out the hard way that your multi-billion kilogram Starship behaves like a truck in mud, slowly tilting and sinking while you watch your only ride fold. Solid ground also isn't always quiet. A planet can look stable from orbit and still be tearing itself apart slowly from the inside. So the next question is, are you building on a rock or on something that's constantly moving and cracking? You answer that with seismology. You drop seismometers, sensitive vibration detectors, onto the surface, sometimes in networks. They listen for quakes and for impacts from falling rocks or meteoroids. We've already seen on Mars that a dead world still has Mars quakes, small but steady as the crust flexes and cools. In this new system, the pattern of quakes tells you a lot. If you see frequent strong events along specific lines, that flags active faults, places where tectonic plates or crustal blocks are slipping by centimeters per year. Build across one of those, and your foundations will crack, your tunnels will distort, and your fuel tanks can rupture. If you hear lots of impacts, especially on worlds near dense asteroid belts, you know the sky is still falling often. That pushes you to put main bases underground or under thick roofs, not out on exposed plains. Seismology also reveals whether the crust is thick and rigid or thin and flexible, which changes how easy it is to dig, mine and tunnel. And on top of rocky worlds, there's a whole other class of targets that look tempting and terrifying at the same time, the active ice worlds. On icy moons, instead of molten rock, you can get cryovolcanism, eruptions of water, ammonia or methane slush. We've already seen this in our system. On Enceladus, jets shoot water vapor and ice grains hundreds of kilometers high at hundreds of meters per second. On Triton and Europa, there are signs of similar activity. In a new system, an icy moon with fresh bright surfaces, fractures and plumes tells you there is interior heat, and probably a subsurface ocean. Scientifically, that is a prime target, potential habitat for life under the ice. Operationally, it's risky. Landing near active geysers means dealing with changing terrain, vents that can open or close without warning, and plumes that can sandblast your equipment or coat it in frost. Your landers have to be designed for cold, for flexing ground, and for periodic showers of ice grains. You have to pick sites far enough from the main vents that you're safe, but close enough that you can tap that internal water and heat. By the end of this stage, you have a clear picture of which places have miniable water and useful rock, which surfaces will actually hold up under your gear, how much the ground shakes, and which ice worlds are alive under their shells. You've narrowed a whole star system down to a handful of viable landing zones and resource nodes. But you still haven't answered the most loaded question of all. If you go down there, are you stepping onto sterile ground or into someone else's biosphere? Before you even think about opening a hatch, you have to know whether the chemistry of these worlds is just geology or already shaped by life. You've found worlds with decent air and useful ice, but there's a bigger risk now, not that the planet kills you, but that you kill something that's already there. Before you send anything down, you have to ask, is this chemistry just rock and sunlight? Or is there a biosphere quietly breathing under these clouds? The first clue comes from atmospheric disequilibrium, gas mixes that should not exist for long without something constantly renewing them. On Earth, oxygen and methane are the classic pair. Oxygen is highly reactive, it likes to rust metals and burn carbon. Methane is easily broken apart by ultraviolet light. In a purely sterile atmosphere, methane gets destroyed in only thousands of years, which is nothing on geological timescales. Yet in our air, you see both percent-level oxygen and tens of parts per million of methane at the same time. The only reason that balance holds is because life, plants, microbes, and everything that breathes and rots keeps pumping them back in. So you point your spectrometers at these new worlds and look for the same kind of unstable combinations. Strong oxygen plus noticeable methane, or oxygen plus other reduced gases that don't play nicely together. You know that no simple, steady geology can keep that up. If you see it, something is working, reacting, cycling, and doing it constantly. That doesn't prove complex life, but it does move you from probably dead rock to something is actively reshaping this air. But gases are not the only way a biosphere shows up from orbit. Life changes the colour of a planet, literally, and you can pick that up if you know what to look for. You measure the planet's reflectance, how much light it bounces back at different wavelengths. On Earth, green plants absorb strongly invisible red light, but then reflect sharply more in the near-infrared just beyond what your eyes see, around 0.7 micrometers. That creates a feature called the vegetation red edge, a sudden jump in reflectivity at that wavelength. Minerals usually have smoother, less dramatic curves. So you watch the planet across its rotation, under different phases and cloud patterns, and you build global colour maps. If large regions on the day side consistently show a sharp reflectance jump at a specific wavelength, or some other strong repeated pattern that doesn't match no minerals, that's a red flag that pigments are at work. Those pigments might be doing photosynthesis, or some alien equivalent, harvesting light in a way that leaves a clear planet-scale signature. You're basically asking, does any patch of this world change colour in a way that screams organised biochemistry rather than random rock? Even then, smart geology and weird chemistry can fake you out. So you go deeper, down to the level of isotopes, to see if the atoms themselves carry a biological bias. Isotopes are versions of the same element with different masses. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. Chemically they behave almost the same, but not perfectly. Life tends to use the lighter versions more easily, because reactions with lighter atoms usually run a bit faster. Over time, biological processes slightly enrich reservoirs of material in the lighter isotopes. On Earth, organic carbon and some gases are measurably richer in carbon-12 compared to volcanic or purely chemical sources. Your orbiters and high-end spectrometers can measure the ratios of these isotopes in gases like carbon dioxide and methane, and in surface materials if you get reflected spectra clean enough. You know what ratios you expect from non-living processes under different temperatures and pressures. If you see a systematic offset across the whole planet, not just a local odd spot, that's another quiet hint that a biosphere has been running for a long time, slowly sorting atoms by mass. But you cannot just shout life every time you see a strange spectrum. Nature has many ways to fake what life does. So the next step is the hard one. You have to prove to yourself that you're not being fooled by weird geology or harsh stellar physics. Volcanoes can pump methane, sulfur compounds, and other interesting gases into the air with not a single microbe. Strong ultraviolet light from the star can drive surface and atmospheric chemistry that produces oxygen from the breakdown of water especially if the planet has lost most of its hydrogen. Large impacts can briefly flood the atmosphere with exotic gases and dust that look odd for a while and then settle out. So for each biosignature candidate you cross-check, you compare gas abundances with thermal maps, with known hotspots and active volcanoes. You model the star's ultraviolet output and see if photochemistry alone can explain what you see. You look at time variation. Does the signal stay stable over years, like a big global biosphere, or spike and fade like a volcanic episode? This is where decades of exoplanet theory finally collide with hard local data. Every model that once lived only in simulations now gets tested against a real alien atmosphere. You will get false positives. You will find planets that look perfect from far away and turn out to be weird but lifeless. But if after all these checks, a planet still shows gas mixes out of balance, surface colours that fit biology better than minerals, and isotopic ratios shifted in the life direction, then the conclusion becomes harder to avoid. You're not alone in that air, and that drops you into the most serious paradox of the whole mission. The moment you are most sure a planet is alive is also the moment when landing there might be the worst idea you could have. Strong biosignatures mean this world is a treasure for science, and maybe a mirror for understanding our own origins. They also mean it has its own ecosystem, tuned to its own chemistry, and extremely vulnerable to whatever you bring with you. Planetary protection rules that started small back in our own solar system, like avoiding accidental contamination of Mars or the subsurface ocean of Europa, suddenly scale up to entire Earth-class worlds light years away. You're forced to shift from asking, can we land, to do we dare land at all? You draw up policies in real time, full sterilization of probes, strict limits on where they're allowed to touch. Maybe a complete ban on human landings for the first generation, or longer, with only high-altitude sampling and remote sensing allowed. That is a hard sell to a crew that has spent their whole lives in transit. But if you get this wrong, you can overwrite a native biosphere with your microbes, or pick up something that your immune systems have never seen and bring it back into your closed habitats. So right at the threshold of first step on an alien world, you're forced to pause. The more alive a planet looks, the more you may have to hold back and treat it as a preserve, not a place to settle. That tension doesn't go away, and if you do find a place where the biosignatures are weak or absent, the air is workable, and the resources are there, that just sets up the next high-risk phase. All the maps and spectra in the world don't change the physics of dropping from orbit into an atmosphere you've never flown through before. So the question turns from, is there life down there, to can your ships and your people survive the first descent through that unknown air without burning up, breaking apart, or disappearing into the dust? You're finally in orbit, but the moment you drop toward the surface, you turn back into a high-speed projectile. Even after all that braking, your landers still hit the top of an atmosphere at several kilometers per second, and the physics there does not care that you're almost stopped. Take a typical entry speed of 7 kilometers per second, about 25,000 kilometers per hour, around 15,000 miles per hour. At that speed, the air in front of your vehicle can't get out of the way smoothly. It piles up and forms a shockwave, a thin layer, where the gas is suddenly compressed and heated to thousands of degrees. Your heat shield doesn't just see warm air, it sees a blowtorch spread over its surface. Peak heat loads hit megawatts per square meter for minutes at a time. That is like having a power plant focused on each square meter of your shield. Your designs draw on everything learned from Mars and Venus. Mars entries showed how thin air gives less braking and lower heating, but for longer. Venus showed how thick air gives brutal heating and pressure very quickly. Here, on a brand new world, those numbers are uncertain. So on the first few entries, you fly with extra margin. You give the heat shield more material, more ablative layer to boil away and carry heat off. You aim for entry angles that are shallow enough to stretch out the heating over time, but not so shallow that you skip out of the atmosphere like a stone and end up in the wrong orbit. Once you're through the worst of the fire, another problem takes over. How do you actually slow from supersonic to zero in an atmosphere you've only sampled from orbit? On a world with thin air like Mars or thinner, Parachutes don't give you much drag. You can fall at hundreds of meters per second and the chute just flaps. On a thick air world like Venus, the dynamic pressure is so high that a parachute deployed too early can rip itself apart instantly. So you tune your systems to the local conditions. You choose fabrics and lines with tensile strengths of hundreds of megapascals, strong enough to take the violent jerk when a supersonic chute opens. You stagger deployments, first small drogues to stabilize, then main chutes at just the right speed and altitude. But chutes alone rarely get you all the way down softly. The last few hundred meters per second are usually killed by retro rockets. Those engines have to throttle with fine control, too little thrust and you hit hard, too much and you hover, wasting propellant, or you blast craters that kick dust and rocks up into your own engines and sensors. On weak surfaces, a hard plume can dig a hole under you and let your lander drop into it, tipping or collapsing a leg. So you shape nozzles and flight software to spread the exhaust, limit erosion, and cut thrust the instant your pads feel solid support. Even if your hardware works perfectly, the atmosphere itself still tries to push you off target. So the next question is, how small can you make the zone of maybe we land here, when every gust and every sensor glitch moves you around? Engineers call this the landing ellipse, the area on the ground where you might touch down given all your uncertainties. Winds, unknown density layers, sensor noise, timing errors all stretch that ellipse. Early Mars missions had ellipses hundreds of kilometers long, meaning we're happy if we hit anywhere in this giant patch. With terrain relative navigation back home, cameras that match surface features to preloaded maps, we push that down to a few kilometers. Your Starship landers push harder. You might be aiming for a narrow plateau between cliffs and old lava flows, or a specific patch of ice in a crater. You want error bars in the tens to hundreds of meters range, not tens of kilometers. So the lander constantly compares what its cameras see to high-resolution orbital images, adjusts its flight path in real time, and even makes last-second lateral moves under rocket power to dodge unexpected hazards. Every meter of extra precision you buy in software and sensors gives you more freedom to choose scientifically rich and operationally safe sites, instead of being forced into bland, flat, uninspiring planes. But the real truth about a planet doesn't hit you until the final seconds, when your pads touch the surface and the accelerometers spike. That first contact with alien soil is your reality check. Sensors in the landing legs record the deceleration profile as each foot hits. If the pads bite into something like firm sand, you see a sharp but limited spike, then a steady load. That corresponds to bearing strengths of tens of kilopascals, enough to hold up heavy hardware. If the soil collapses, like talcum powder or very loose dust, you see a slower, drawn-out deceleration as the leg sinks deeper, and the load gets shared in strange ways between legs. That tells you the regolith is weak, low cohesion, high porosity. Every millisecond of that data feeds back into your surface models. It changes where you dare to send the next lander, and how you'll design foundations for future structures. If a small robotic probe already sinks more than expected, you know not to trust that spot with a human-rated vehicle. And just when you think you're done with surprises, you get hit by something that seems trivial and turns out to be one of your worst long-term enemies, ultra-fine dust. Fine grains, micrometers across, behave differently from sand and gravel. Electrically charged by sunlight and friction, they can cling to almost any surface. We saw this with lunar dust during Apollo. It stuck to suits, joints, and radiators and was hard to get off. In low gravity and thin air, rocket plumes can loft this dust to great heights, sometimes kilometers above the ground. Those clouds then drift and settle everywhere. Each grain is like a tiny piece of sandpaper. Over time, they abrade seals, scratch windows, and eat away thermal coatings. They creep into hinges, bearings, and connectors, and they foul radiators so badly that the panels can no longer dump heat efficiently. So from the very first landing, you monitor where dust ends up on your vehicle. Cameras watch how plumes move. Filters and sample plates collect particles so you can study their size, shape, and how easily they charge and stick. That early dust data directly changes your plans for habitats and vehicles, Do you need airlocks with aggressive dust traps? Do you need external systems designed to be easily brushed or blasted clean? Do you need to bury radiators or aim for designs that run hotter so they can tolerate coatings? Dust decides. By the time the first lander is sitting still and sending back images and sensor logs, you've crossed one of the biggest physical thresholds in the whole mission. You went from interstellar flight to a human-scale surface, and the planet did not kill the hardware on contact. But as soon as those first footprints, human or robotic, are pressed into that soil, a different kind of problem starts. You're not just landing machines now, you're landing a society that still thinks of home as a star light years away, with people back there expecting answers. And for the first time, you have to run that society in a place where every message to Earth takes years to arrive and every reply takes years to come back. So the question shifts from pure physics to something just as hard. How do you build and hold together a civilization when the speed of light itself turns every conversation with home into a one-way letter with a decade-long delay? You can stand on an alien world, send a message to Earth today, and know that no living person there will ever read your reply to their answer. That is the communication reality the moment you arrive at another star. Light speed is no longer an abstract constant, it's a hard wall. If you are 10 light years away, even a perfect laser signal travelling at 300,000 kilometers per second, about 186,000 miles per second, still takes 10 years to get home. Any answer takes another 10 years to come back. That is a 20-year round trip for a single question. At 30 light years, the round trip climbs past 60 years, longer than many human careers and not far off a human lifetime. This delay is not like a bad phone line. You cannot fix it with better hardware. You can throw bandwidth, power, and bigger antennas at the problem, but not speed. That means your colony, your Starship society, cannot run by talking to Earth for guidance. You cannot ask, should we land here, and wait? You cannot vote on a big policy and expect Earth to confirm it. By the time an answer arrives, everyone who asked the question may be old or dead. So you are forced into a level of autonomy no human culture has ever really dealt with. You get one big upload of values, laws, and blueprints from Earth before you leave, maybe a few updates as you accelerate. After that, you're basically on your own. That pushes you toward conservative decisions in some areas and rapid local evolution in others. The physics of light speed quietly turns your new system into a separate civilization, whether anyone wanted that or not. You still send messages, of course, but now the question becomes, how do you push those limited signals through space efficiently enough that anyone can hear you at all? You won't use big fuzzy radio broadcasts the way we do between planets at home. Spreading a radio signal in all directions at tens of light years means the power per square meter at the receiver is microscopic. Instead, you tighten the beam. You likely use lasers at optical or near-infrared wavelengths, focused through a transmitting array, maybe 10 meters across or bigger. With that size, you can squeeze the beams spread down to microradians, millionths of a radian. Over tens of light years, that still means the beam widens to a spot millions of kilometers across, bigger than the orbit of Earth around the Sun, but that is incredibly tight by interstellar standards. Even with that focus, space eats your signal. At 30 light years, the round trip climbs past 60 years, longer than many human careers and not far off a human lifetime. This delay is not like a bad phone line. You cannot fix it with better hardware. You can throw bandwidth, power, and bigger antennas at the problem, but not speed. That means your colony, your Starship society, cannot run by talking to Earth for guidance. You cannot ask, should we land here, and wait? You cannot vote on a big policy and expect Earth to confirm it. By the time an answer arrives, everyone who asked the question may be old or dead. So you are forced into a level of autonomy no human culture has ever really dealt with. You get one big upload of values, laws, and blueprints from Earth before you leave, maybe a few updates as you accelerate. After that, you're basically on your own. That pushes you toward conservative decisions in some areas and rapid local evolution in others. The physics of light speed quietly turns your new system into a separate civilization, whether anyone wanted that or not. You still send messages, of course, but now the question becomes, how do you push those limited signals through space efficiently enough that anyone can hear you at all? You won't use big fuzzy radio broadcasts the way we do between planets at home. Spreading a radio signal in all directions at tens of light years means the power per square meter at the receiver is microscopic. Instead, you tighten the beam. You likely use lasers at optical or near-infrared wavelengths, focused through a transmitting array, maybe 10 meters across or bigger. With that size, you can squeeze the beams spread down to microradians, millionths of a radian. Over tens of light years, that still means the beam widens to a spot millions of kilometers across, bigger than the orbit of Earth around the Sun, but that is incredibly tight by interstellar standards. Even with that focus, space eats your signal. Dust, slight pointing errors, and the inverse square drop in intensity mean that to push even a few kilobits per second across that gap, you may need transmitter powers in the megawatt to gigawatt range. That's on the scale of large power plants just for a single communication link. You build enormous stable laser platforms near your star, powered by fusion, solar swarms, or both, and you lock them onto Earth's predicted position years in advance. That's the physics side. The next problem is more abstract but just as hard if every bit costs that much power and engineering. What do you actually put in those bits? You cannot stream your daily life. There is no real-time video call to Earth, no casual browsing of news in both directions. Every bit is expensive, so you send the highest value content you can compress. That means raw science data sets that can't be reconstructed any other way. It means full genomes of new organisms, so biologists back home can study them. It means libraries of local history, legal decisions, culture and art packed down with heavy compression. You think in terms of information theory, how many surprises per bit does this message carry? A boring, predictable signal carries almost no new information. A highly structured but previously unknown dataset carries a lot. You prioritize transmissions that change Earth's understanding the most per bit. A summary of a whole decade of colony might make more sense to send than hours of unedited legislative meetings. A compressed, annotated map of the whole star system beats raw imaging frames. You even need to send the metadata, the instructions on how to decode and understand your own formats, because by the time your message arrives, software and standards on Earth may have changed completely. While that long, thin thread to Earth runs in the background, you still need fast, dense communication locally. So the obvious question is, what does an internet look like when even the nearest planets are light minutes apart instead of milliseconds? Inside the new system, light travel time is still a limit, just on a smaller scale. At 1 astronomical unit, the average Earth-Sun distance, light takes about 8 minutes to travel one way. At 5 astronomical units, around the orbit of Jupiter, that becomes about 40 minutes. A message between an inner planet and an outer mining outpost can have a round-trip time of over an hour. Signals between orbit and the surface are faster, but still take a noticeable fraction of a second once you factor in routing and processing. You design your network around that delay. Forget the idea of instant ping. Control systems for landers and tugs are mostly local or predictive, not joystick-operated from far away. Your protocols assume that acknowledgements will come late or might not come at all for a while. You buffer data heavily, you use store and forward routing, and you write software that keeps working even if the link to higher authority drops for hours. It's like running an internet where local servers talk in milliseconds, but interplanetary backbone links have pings of hundreds or thousands of seconds. Socially, that changes habits. People stop expecting instant replies. Meetings between bases happen on long delay, more like exchanging long voice messages than chatting. Whole designs and project plans are pushed in batches, not trickled. The entire system learns to work asynchronously because the speed of light is baked into every packet. All of that is technical and solvable. The part you can't code away is what this does to people. So the last question in this chain is the most human. How does a culture function when the distance to its origin is measured not just in kilometers, but in whole human lives of delay? For the first generation, many of the people in your Starship society were born under the old idea of Earth as home. They grew up with images, languages, and stories from that world. But as years pass and light-lagged messages crawl back and forth, those links stretch thin. A child born in the new system might send a "Hello Earth" message at age 5, get a reply when they're 15, answer again and see the follow-up maybe in their mid-20s or 30s. That is not a conversation, it's more like exchanging time capsules. Friendships, family ties, even conflicts with Earth move at that pace. By the time an argument crosses the gap, the people who started it might not hold power anymore, or might be dead. Relativity stops being a chapter in a physics course and becomes something they feel in their bones. Space and time are locked together in a way that dictates how relationships can and cannot work. So your arrival at another star doesn't just expand where humans can stand. It reshapes how long human stories take to unfold. You become a civilization that has to think in decades and generations just to finish a single back and forth with its own parent world. And even as you're dealing with that slow-motion connection, another, much more immediate problem is waiting right in front of you. The bodies that came through interstellar space to build this new society are not the same as the ones that left Earth. Bones, muscles, DNA, sleep cycles and minds have all been reshaped by years in microgravity and radiation. So the next challenge is as personal as it gets. After deep space has rewired your biology and psychology, can human bodies and minds actually handle stepping into this new gravity, this new day-night cycle, this new sky without breaking? You step off the ship and gravity hits you like a diagnosis. Years or decades in microgravity have reshaped your body quietly day after day. Without very aggressive exercise, bone can lose 1 to 2% of its mineral density per month in weightlessness. Muscles in your legs, back, and core shrink because they haven't had to hold you up. Now you're in a field of 0.8 G, 1 G, maybe 1.5 G. Every kilogram of your body suddenly weighs more again. Your heart has to pump harder to push blood up to your head. Your joints feel loads they haven't carried in years. You don't just walk out and get to work. Rehabilitation becomes planetary-scale physical therapy. At first, many people use exoskeletons or powered braces to help with load bearing. Habitats set up gravity ramps, areas at lower effective G, where you can retrain slowly, then move up to full gravity as your bones and muscles adapt. Medical teams track bone density with scanners, monitor heart function, and tweak exercise plans constantly. Even just climbing a few stairs is scheduled and supervised for some, because a simple fall in high gravity with fragile bones can mean fractures that are hard to treat. And all that is on top of another invisible injury everyone carries, the radiation the journey has already written into your DNA. Even with good shielding, the trip probably gave you cumulative doses of radiation in the hundreds of millisieverts, maybe more if storms or hardware failures pushed exposure up. Some cells repaired that damage, some didn't. Double-strand breaks in DNA, subtle mutations in stem cells, and damaged tissue in bone marrow and organs all come along for the ride. That damage does not go away when you step into a new star's light. So you treat your first generation like long-term patients as much as pioneers. You arrive with gene repair therapies, tools that can target and fix some classes of mutation. You unpack stem cell banks, preserved lines of your own cells and engineered backups to rebuild damaged tissue and support bone and blood regeneration. You roll out cancer screening tech that's much more aggressive than anything you'd use for a normal population back on Earth. Regular whole body scans, blood tests tuned to catch early signs of leukemia and other radiation-linked cancers. Part of your new star system, especially in the early years, is basically a triage ward for interstellar travelers, stabilizing the bodies that carried you here before they break under the combined load of past radiation and new gravity. While all that is happening physically, your internal clocks are also being forced to reset. Your whole sleep-wake system was trained under one pattern in the ship, and now the sky above you is running on a different schedule. Human circadian rhythms, the internal day-night cycle, naturally run a bit over 24 hours. We know this from isolation studies where people kept no external time cues. On the ship, you probably locked that rhythm to an artificial 24-hour day with lighting and schedules. Now, your chosen world might spin once every 26 hours or 9 hours or something in between. Sunrises and sunsets come at the wrong times for your biology. Left alone, people drift, some staying up longer, some snapping awake long before dawn, sleep debt building quietly. You have to reprogram that. Habitats use engineered lighting that shifts colour and intensity aggressively, blasting bright blue-weighted light during your new morning, cutting that back at evening and dropping toward red, dim light at night. Work shifts are set to force consistent cycles. In some cases, you use drugs that tweak melatonin and other hormones to push people's internal clocks toward the local day length. There's no option to ignore it. A population with scrambled sleep is a population with higher accident rates, weaker immune systems, and more mental health problems at the exact time you need everyone sharp. And speaking of mental health, the psychological re-entry from deep space to a horizon and a sky is its own shock. For years, maybe decades, your universe was a closed ship, metal walls, a fixed number of people, recycled air, and stars as distant, untouchable lights. Studies on Antarctic winter crews and astronauts on the International Space Station already show that even a few months of confinement and isolation can cause stress, mood swings, depression, and conflicts. You've taken this to an extreme. Entire life stories have played out in a cylinder a few hundred meters long. Then one day, there's a real sky overhead. Weather. Clouds. A horizon so far away that your brain has to relearn depth. For some, that's pure relief. For others, it's terrifying. Open spaces can trigger anxiety in people used to walls. Noise from wind, alien wildlife, or just distant machinery can feel overwhelming after the controlled quiet of a ship. People have to unlearn spaceship thinking, the constant background assumption that every mistake kills everyone, and adjust to environments where you can walk outside in a suit and not immediately die if a light flickers. You plan for this the way you plan for any other engineering problem. You bring psychologists, counselors, and social structures designed for re-entry. You use graded exposure, starting people in domes and tunnels with clear views but controlled access to the open, then letting them range farther as they're ready. You watch for signs of breakdown and burnout, not just in obvious patients, but in leaders and critical technical staff, because a mentally overloaded habitat manager can be as dangerous as a failing reactor. And under all of this is a quieter, deeper shift, one you can't fix with therapy or training. If multiple generations were born in transit, the place they call home is not Earth and not this planet. It's the ship itself. For them, the interstellar journey wasn't a trip, it was the entire world. Culture, language shifts, myths, and stories all grew in a moving, human-made environment. Arrival was a promised future, something their grandparents talked about. Now it's here. The founding myth has concluded. That can feel like victory, or like having the ground pulled out from under their identity. They might not see this planet as a dream. They might see it as the thing that will break apart the only society they have ever known. You watch in real time what happens when a mobile, self-contained civilization slams into a solid, immovable piece of rock and sky. Some people will rush to build cities on the surface. Some will fight to keep the ship culture alive in orbit, refusing to ground themselves. Some will split their loyalties, creating new cultural rifts that Earth never had to deal with. Every decision you make about where people live, how fast you push surface settlement, and how much you preserve shipboard ways of life, feeds straight into whether this new system becomes a coherent society or fragments into competing worlds within a world. By the time you stabilize bones, patch DNA, retune sleep cycles, and help minds adjust to the new sky, you're already doing more than survival. You're bending human biology and culture to fit a new star. And once you start doing that successfully, the logic of the mission shifts again. This can't stay a one-off stunt. If you can take one system and make it livable, the next question is unavoidable. How do you turn this foothold into a true industry of expansion, with habitats, fuel, and factories that let you launch from here to the next stars? And the next, until this single arrival becomes the seed of a whole network spreading through the galaxy. You can't keep living here by burning through what you brought. Shipping mass from Earth across light years is effectively impossible, so in this system, use local stuff or die isn't a slogan, it's a law. That starts with in situ resource utilization, ISRU. Every kilogram of structure, fuel, air and water has to come from local rocks and ice. If your prospecting shows regolith with 10% water by mass, that's gold. 100 tons of that dirt gives you 10 tons of water, about 10,000 litres. You bake and process it, filter out dust and salts, and that water turns into everything: drinking supply, air, by splitting it into oxygen, hydrogen and recombining as needed. And dense radiation shielding you can stack around habitats. Run it through the electrolysis, and it becomes rocket propellant, liquid hydrogen and liquid oxygen, ready to feed landers and tugs. Suddenly, the question for every landing site is simple: how fast can we turn that ground into air, fuel and shielding? But none of that works if you can't power it. So the next issue is just as brutal. How do you build a stable power grid under an alien sun when you can't plug into anything you brought? Near 1 astronomical unit from a sun-like star, you get about 1.3 kilowatts of solar power per square meter at the top of the atmosphere. With solar panels at 20 to 40% efficiency, each square meter nets a few hundred watts in good conditions, maybe enough to run a bright light bulb and a laptop. That sounds tiny until you scale it. A solar farm 1 kilometer by 1 kilometer is 1 million square meters. At a few hundred watts per square meter, that's hundreds of megawatts of power, enough to drive life support, mining gear, industry and your first communication lasers. So you cover crater rims, flat plains and orbital platforms with panels. You link them into microgrids that can isolate during storms and reconnect when the sky is clear. You build massive battery banks, flywheels or hydrogen storage so that day-night cycles and dust storms don't drop your systems. Farther out, where the solar flux falls off fast, solar becomes weak. There you switch to fission reactors fed by uranium. You mine locally, fusion if you've cracked it, or even beamed power. Lasers or microwaves fired from inner system stations to wreck tenor farms around dark outer moons. Now you've got water and electricity. The next question is, do you really want to haul metal pressure vessels from orbit forever? Or can you literally print your buildings out of the ground you're standing on? You start building with regolith and ice. 3D printers and sintering rigs melt or fuse local dust into solid blocks and beams. On a low-gravity moon, those pieces can span tens of meters without collapsing, because their own weight is much smaller than on Earth. You design domes and tunnels that put meters of rock and compacted regolith over your heads. That mass slams incoming cosmic rays and solar particles, cutting radiation levels inside by factors of 10 to 100 compared to the surface. You can also freeze water into ice bricks, reinforced with fibers or mesh, and use them as transparent or translucent walls in shielded areas, combining structure with more radiation protection. These structures don't look like glass towers. They look like berms, bunkers and buried halls, but they're cheap in the only currency that matters out here: imported mass. Sobs. Every ton of regolith you use as a wall is a ton of steel you don't have to ship or smelt. Once you have local fuel and solid shelters, you're ready for the real backbone of a multi-planet system, logistics. So the next thing you solve is, how do you move stuff around without burning insane amounts of propellant every time? You turn water and other volatiles into fuels, then move those fuels into orbit and beyond. Ice mined from moons and asteroids gets melted, purified, cracked into hydrogen and oxygen and liquefied. Tankers haul it up to orbital fuel depots. You put those depots in strategic places, low orbit around key worlds, Lagrange points where gravity lets you park cheaply, and along standard transfer orbits between planets and moons. Delta. V-budgets, the speed changes you need to move between bodies, define your trade routes. If going from a resource-rich moon to a major habitat costs only a few kilometers per second of delta V, chemical rockets using local propellant are enough. Where gravity wells are deep, like big super-Earths, you look at space elevators, long tethers dropping down from orbit, or mass drivers, electromagnetic launch tracks that throw cargo up without using chemical fuel on the ground. Over time, you build a map of cheap and expensive moves, and your whole industrial web grows along the cheap paths, just like shipping lanes and railroads on Earth. All of this still needs a manufacturing base. You can't import factories by the dozen, you arrive with a handful at best. So the next challenge is harsh and simple. How do you bootstrap an entire industrial ecosystem from almost nothing? You start with seed factories, maybe tens of tons of machine tools, robotic arms, metal and ceramic 3D printers, electronics fabs, and raw stock. At first, they only build spare parts and basic components, keeping your initial landers and habitats running. As you mine more metals and refine more silicon and other materials, those same factories start printing their own upgrades, new printers, better machine tools, more robots. You deliberately design machines that can build most of their own replacements given time and raw feedstock. Once that loop closes, growth becomes multiplicative. A factory line that could produce one copy of itself every few years turns one plant into two, two into four, and so on. Within decades, a single small asteroid a few kilometers across can be carved out and rebuilt as a cluster of rotating habitats, with total internal living volume larger than all skyscrapers on Earth combined. Its surface can host railguns, fuel depots, power towers, and shipyards. At that point, you've done more than survive. You've turned "we arrived at one star" into "we have a working industrial civilization anchored to the system." And once that engine is running, one more question starts to push everything else aside. If you can spin up full industry here, if you can mine, build, power, and launch without help from Earth, what does that do to our picture of the galaxy itself? Does this stay a lonely outpost? Or does it become the first node in a spreading web of probes, habitats, and new civilizations, each one rewriting our estimates of how common life and intelligence really are? You can land, mine, and build, but you still don't know what kind of story this star system has already lived through. Before you call it home, you need to know if you've walked into a young, unstable neighborhood, or an old, battered one that's somehow still hanging on. You start with the star itself. Its light is a record of its age and its birth environment. By splitting the spectrum into very fine wavelengths, you measure how strong different absorption lines are, especially for elements heavier than helium, what astronomers call metals. High metallicity, lots of iron, silicon, and heavier stuff means that this region of the galaxy has been seeded by many past supernovae. Low metallicity means the opposite. Fewer earlier generations of stars exploded here before this one formed. On top of that, you watch tiny oscillations in the star's brightness and spectrum, its vibration modes. That's asteroseismology, effectively listening to starquakes. The pattern of those modes lets you estimate the star's age, maybe to within 10 to 20%. Is this a 1 billion-year-old baby star that's just settling down, or a 9 billion-year-old elder near the end of its stable life? The answer tells you how long its habitable zone has been steady, and how much time any potential biosphere has had to evolve. Once you've pinned down the star's rough age and metal content, the next question is, how has that age actually played out on the surfaces of its planets and moons? You answer that with craters. Every impact leaves a scar, and together they form a planetary diary. From orbit, you count craters per square kilometre, and sort them by size. A surface saturated with craters larger than a kilometre across, half a mile, means it's old and has been sitting exposed for a long time. Smooth plains with very few craters suggest more recent resurfacing by lava flows, glaciers, or tectonic activity that wiped the slate clean. You build crater maps for multiple worlds in the system. If several bodies show a spike of big basins with similar ages, that hints at a system-wide bombardment event. Maybe when giant planets migrated and flung comets and asteroids everywhere. Differences between inner and outer worlds tell you how debris belts shifted when things calmed down, and whether there were long, quiet periods when life could evolve without being reset by constant impacts. Those crater counts set up a timeline in broad strokes. To sharpen it into real dates, you need clocks built into the rocks themselves. That's where isotope ratios become time markers. Certain radioactive isotopes like uranium and potassium decay into stable daughters, like lead and argon, at known rates. When molten rock cools and solidifies, it locks in a starting ratio. Over time, the parent decays and the daughter builds up. By measuring both in a rock sample, a lab can back-calculate how long it's been since that rock last melted or cooled through a critical temperature. This is uranium-lead dating, potassium-argon dating, and similar methods. On Earth, we've used these to trace a 4.5 billion year history. In this new system, you do the same. You grab samples from ancient highlands, young lava plains, impact melt sheets, and sedimentary layers. If you find crusts significantly older than Earth's, you're looking at planets that had time to settle long before our own. If you find that solid crusts only appeared much later, or that they've been recycled aggressively, that shifts your sense of how typical Earth's timing really is. Once you have ages, you can start asking deeper questions. Did any of these worlds hold stable oceans and climates long enough for complex life to be likely? Or did their own interiors and skies sabotage them? You look for tectonics, oceans, and signs of long-term climate regulation. Plate tectonics, like on Earth, cycles carbon between the crust and atmosphere. Subduction zones drag carbon-rich rocks down. Volcanoes bring carbon dioxide back up. Over hundreds of millions of years, this works like a thermostat, helping keep temperatures in a range where liquid water can stick around. From orbit, you search for long, linear mountain chains, deep ocean trenches, and mid-ocean ridges in topographic maps. Gravity data reveals dent, sinking slabs and upwelling mantle plumes. If you see active plate boundaries and evidence of oceans that have existed for billions of years, that's a strong sign of climate stability. Now, match that with your biosignature search. If a planet shows a long, stable ocean history, moderate irradiation and balanced greenhouse gases, but no sign of complex life in its rocks or air, that seriously challenges the idea that evolution naturally marches toward complexity given enough time. It suggests that even with perfect conditions, complex multicellular life might be rare or slow. Of course, stability is only half the story. The other half is catastrophe. Even a well-tuned climate can be wrecked by rare violent events. So the next question is, how often has this system slammed its own reset button? You start hunting for evidence of past mass extinctions and global crises in the rocks. A thin layer rich in iridium, an element more common in asteroids than in crustal rock, spread across a whole planet, points to a giant impact like the one that helped end the dinosaurs on Earth. Layers packed with shocked quartz and little glassy spherules mark the same kind of event. Huge, stacked lava flows, flood basalt stretching across continents, signal massive volcanic outbursts that can poison atmospheres and drive climate swings. In sedimentary records, you look for sudden changes in fossil types or chemical markers that flag rapid shifts in temperature or ocean chemistry. You also search for glacial deposits at low latitudes, signs of past snowball phases where ice reached almost to the equator and the planet nearly froze solid. Count how often these things happen and when. A world with one or two big hits spread over billions of years gives life long windows to diversify between disasters. A world hammered every few tens of millions of years by planet-scale eruptions or impacts might never let complex ecosystems stabilize. Across the system, you compare these histories. Did inner rocky worlds share the same catastrophe schedule? Or did some get spared by chance orbital alignments or protective giant planets? By the time you're done, you've built a deep timeline for this star system. You know when the star formed and how metal-rich it is. You've dated the birth and resurfacing of crusts, traced bombardment eras, checked for long-lived oceans and active tectonics, and logged every major catastrophe you can find. You've essentially done cosmic archaeology, reconstructing billions of years of history from light, craters, and isotopes. And that leads straight into the biggest question hanging over the whole project. Once you truly know how one other system has played out, from star birth to present day, how much does that single data point force us to rewrite our estimates about life and intelligence in the galaxy? Does this system make us think we're common, rare, or almost impossibly lucky? You've dug through this system's rocks, air, and radiation, And at some point you have to face what it all means for the big question people back home have argued about for a century. How common are we, really? The tool everyone talks about is the Drake equation. It's not a strict formula, it's a structured guess. You take the rate of star formation, multiply by the fraction of stars with planets, then the fraction of those with habitable zones, then the fraction that actually develop life, the fraction that evolve intelligence, the fraction that build technology, and the average lifetime of those civilizations. For decades, almost all of those terms were educated guesses, with huge error bars. Now, for at least one other sun-like star, you finally have a real outcome, not a guess. Did this system produce life? If yes, what kind? Did any of that life become complex, organized into large bodies? Did any of it build tools, cities, or machines that left a trace you can still see? Those are direct answers to several of the Drake factors, all in one place. It's just one data point, but in a universe where you used to have 0 data points outside the solar system, one is a big jump. Start with one of the most unsettling outcomes. What if you find a perfect-looking world that's completely empty of life? Picture a planet in the habitable zone with liquid water, a thick but balanced atmosphere, and a climate that your models say has been stable for billions of years. You've checked for biosignatures in the air, scanned the surface for weird colours, sampled rocks and ice, and looked at isotopes. Everything says chemistry only, no biology. No microbes building up strange gases, no layered fossils in sediments, no biological imprints in carbon ratios. On paper, that world is an Eden, warm enough, stable enough, and calm enough to host life for a very long time, but it didn't. That hits the Drake equation hard. The term for fraction of habitable worlds that actually develop life at all suddenly looks lower. Optimistic ideas that wherever water sits long enough, life just appears take a hit. Even one clear sterile Eden forces a correction because it proves that perfect conditions are not a guarantee. Back home, people who argued that the galaxy must be full of biospheres now have to explain why one of the best case systems you reached never fired that starter gun. The picture shifts if you find life, but only at the simplest level. Suppose your instruments pick up strong signs of a microbial biosphere. Maybe there's methane being produced in a way that matches microbial chemistry, or you land and find mats of simple organisms under rocks or ice. The atmosphere is in chemical disequilibrium that fits biology. Isotopes are skewed in a lifelike way, and lab tests on samples show replication and metabolism. But there's nothing multicellular. No large fossils, no complex food webs, no forests, no animals, no big organized organisms at all. On Earth, life stayed single-celled for more than 1 billion years before complex forms appeared. If this other world is the same age or older and it's still stuck at microbes, that suggests the real bottleneck isn't going from no life to simple life, but from simple life to complex life. In Drake terms, the fraction of life-bearing worlds that go on to develop complex multicellular ecosystems might be far lower than you hoped. And if complex life is rare, then the fraction that ever gives rise to intelligence and technology shrinks even more. In practical terms, finding a thriving microbial planet with no complex organisms could slash the expected number of technological civilizations in the galaxy by orders of magnitude, just based on that one comparison. There's a third possibility, and it's the one that flips the whole discussion from pessimism to something much stranger. What if you find evidence of technology that is not yours? That could be obvious, like picking up a narrowband radio signal with a clear artificial pattern, or seeing a laser line at a wavelength that makes no natural sense. It could be structural, like stumbling on a derelict station in orbit, or spotting objects in unnatural engineered orbits. It might even be chemical, like finding industrial pollutants or engineered isotopes in an atmosphere that can't be explained by volcanoes or normal chemistry. Even one solid techno-signature, one piece of real alien hardware or signal, slams several Drake terms upward. The fraction of stars with intelligent civilizations doesn't just become non-zero, it becomes at least 2 in the small sample we've checked. The fraction that developed technology over cosmic time suddenly looks much higher, because now you have independent proof that technological civilizations can arise at more than one star. But a new question jumps in immediately. How long do those civilizations last? If what you see are ruins, dead stations, or fading signatures with no active maintenance, then yes, tech appears more often than we thought, but maybe it also dies out quickly. If you catch a live signal or active structure, you're looking at a neighbour, not a ghost. And the term for average lifetime of a technological civilization has to be at least as big as the time between when they started transmitting and when you arrived. Whatever you find, Earth doesn't just shrug and file it away. Statisticians and modelers back home feed your data into Bayesian updates, a structured way of changing your probabilities when new evidence arrives. Before you launched, people had prior beliefs. Some thought life is common, others thought it's rare, some thought intelligent life is nearly unique. Each of these beliefs had a probability attached. Your findings act like evidence. If you report a sterile Eden, the probability weights shift toward models where life is hard to start. If you report microbial-only worlds, weights shift toward microbes are easy, complex life is hard. If you report a live or dead technological civilization, many previously low probability models where intelligent life is fairly common suddenly gain a lot of weight. This isn't just academic. Those updated odds feed back into where we send the next missions, how we design searches for signals, and even how we think about long-term risks to our own civilization. Are we likely to be alone for a long time? Are we just one of many but far apart? Or are we stepping into a galaxy that has already seen many civilizations rise and fall? Your arrival at this one star doesn't just add new lines to a textbook, it rewrites the background odds behind every story we tell about our place in the universe. And once you've made that leap once, from pure theory to hard data, the pressure to do it again gets intense. Because if a single system can swing our estimates this much, the next obvious step is to stop thinking in one-off expeditions and start thinking in terms of a network, multiple star systems, multiple probes, all feeding back into a growing galactic scale picture. So the final question becomes, now that you've proved a starship can arrive, break, map, land, build, and rewrite our cosmic statistics, how do you turn this into a repeatable process? A wave of expansion that links many stars together into something bigger than any one civilization or planet. You thought the hard part was getting one starship to one star, but as soon as you have mines, factories, and power here, that first crossing stops being the main event. It becomes your new starting line. Once local industry is running, launch economics flip. On Earth, you had to climb out of a deep gravity well, 11 kilometers per second just to reach orbit, burning enormous stacks of propellant. Here, you can build launch pads on low-gravity moons and small asteroids where escape speeds are tens to hundreds of meters per second instead of kilometers per second. A few dozen meters per second is walking speed for rockets. That cuts fuel needs by orders of magnitude. So you start building new probes. Not 1,000-ton starships, but lean, specialized interstellar craft a few tons each. Maybe they use compact fusion drives. Maybe you push them with beamed power, lasers or microwaves from huge stations in this system, pushing lightweight lightsails up to 10 or 20% of light speed again. With factories and fuel on site, you can afford to launch one of these every few years. Each one targets a different nearby star, 10, 20, 30 light years away. Suddenly this system isn't just a destination, it's a launch pad, seeding the volume around it with new expeditions. And if you're willing to hand more of this process to machines, the pace can go from steady to explosive. If you design full self-replicating probes, von Neumann machines, you take the bootstrapping logic you used here and wrap it into an autonomous package. Each probe carries enough hardware and software to mine a target system's asteroids, build local factories, assemble more probes and launch them onward. Even at a modest cruise speed of 0.1 times light speed, about 30,000 kilometers per second, around 18 million miles per hour, a probe can hop from star to star. Daisy chain that over millions of years, and exploration becomes exponential. Each new system can send probes to several more. The Milky Way is about 100,000 light-years across. At 10% of light speed, a single straight-line trip across would take about 1,000,000 years. Give your network tens of millions of years, and in principle, a wave of self-replicating machines could map the entire galaxy, cataloguing stars, planets, and maybe other civilizations. That timescale is tiny compared to the age of the galaxy itself, which is on the order of 10 billion years. Once you start this process, the real question is not, can it reach everywhere, but who, if anyone, chooses to stop it, and where? While the machines expand, the people do something more complicated. Every time humans or their descendants arrive in a new system, they repeat the same physical pattern: deceleration, scan, landing, adaptation. But with light-year distances and decade-long communication delays, each colony's culture starts to drift. After a few hundred years, the population here in your first colony will not quite match Earth. Language shifts, laws adapt to local conditions, technology branches in different directions. Now imagine a third system colonized by ships from here rather than from Earth. Those people inherit not Earth's culture directly, but your local version, already changed. Add in local biology, new gravities, and possibly genetic tweaks to handle different environments, and the divergence accelerates. You end up with a patchwork of human and post-human cultures. System number 3 might be genetically adapted to higher gravity. System number 4 might live mostly in rotating habitats and rarely touch planets. Some might keep close emotional ties to Earth, despite the time lag. Others might cut that link almost completely and see themselves as something new. The human footprint stops looking like a uniform spread and starts looking like a fractal, a branching pattern of related but independent civilizations, all sharing an origin but no longer sharing a single identity. As more systems industrialize, another threshold gets crossed. Your civilization's total energy use starts to show up on galactic scales. Each system builds infrastructure, gigawatt-class communication lasers, terawatt fusion plants, maybe even partial Dyson structures, swarms of power collectors around their stars. Each of those takes a slice of starlight and converts it into organized work, then waste heat. From outside to a distant observer with the right instruments, parts of a spiral arm that used to glow only with natural starlight begin to show excess infrared, radio patterns, and unnatural beams. If any other civilization is watching, this is when they see you, not as a single-odd radio source, but as a spreading network of systems that are clearly doing engineering on stellar scales. Your beamed sail arrays and interstellar communication links become detectable. Your partial Dyson swarms tweak the brightness curves of their host stars. You move from being one biosphere among many to being a visible modifying agent in the galaxy's structure. And all of that brings you back to the original question in a very different light. What actually happens when a starship finally arrives? On the surface level, you've seen it. The ship closes on the target, solves the navigation nightmare of hitting a moving star, kills a fraction of light speed without tearing itself apart, crosses into a new heliosphere, maps planets, picks safe orbits, checks atmospheres and radiation, finds landing sites, survives the first descent, and starts turning local rock and ice into habitats, fuel, and factories. It rebuilds bones and mines for new gravity and new skies. It sets up slow, thin links back to Earth. But in cosmic terms, arrival is not the end of a journey. It's an inflection point. It's the moment a species stops being tied to one fragile biosphere and starts playing on the timescales and structures of the galaxy itself. From that point on, every choice you make, where to build, where to launch, what to seed with machines, what to leave untouched, feeds into a process that can reshape not just one system, but many. The shocking part isn't that you reached another star, it's that from here on out, the galaxy is no longer a distant backdrop in your textbooks. It's your new local neighborhood. All the things we used to call long-term cosmology, stellar lifetimes, galactic rotation, the rise and fall of civilizations, turn into your day-to-day engineering problems. That's what really happens when a starship finally arrives. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.